Okay, continuing our discussion about using standard heats of formation in calculations of enthalpy changes for various kinds of processes. So the way we're going to end up using these standard heats of formation is in this relationship. It's based on Hess's law, where the sum of the heats of formations for a series of the products of a reaction, subtracted from that the sum of the heats of formation of the reactants in a process, will give you the standard heat of reaction for an overall process in a generic sense. A plus B can make C plus D. And so the way we do this is that this overall enthalpy change is going to be the combined heats of reaction for the products, where you have to use their stoichiometric coefficients in there because all of these heat changes are per mole, so you've got to include those stoichiometric coefficients. Subtract from that the combined heats of formation of the reactants A and B here, again using their stoichiometric coefficients. And oh my goodness, there's a lot of things to pay attention to do these accurately. So let's try some examples. So calculating a delta H, in other words, enthalpy change, standard enthalpy change for the combustion reaction of methane, given some heats of formation, the heats of formation for methane, for CO2, for water, and the combustion reaction is where you combine any carbon-containing compound, typically hydrocarbons, with oxygen to make CO2 and water. Now remember, the equation that we're going to be thinking of is the overall enthalpy change that we're looking for a reaction will be the heats of formation for the products, subtract from that the heats of formation of the reactants combined. All right, ready for some steps? The balanced equation is shown here. You have to have a balanced equation because we're going to need to pay attention to the coefficients on water and oxygen to get this right. Okay, here's the reaction again. And here are all the steps, and I'm going to lay them out here. You'll have to stare closely to make sure you see all the pieces. So the heats of formation of the products comes first. So the products are the CO2 and water. And the heats of formation for those two things are in here in our list. So the heat of formation of CO2 will be first, and the heat of formation of water, but times 2 for the balanced equation. Subtract from that the heats of formation from the reactants. And the reactants are methane and oxygen. Well, the heats of formation of methane is provided, but the heat of formation of oxygen is not in this list. Oh, but we don't have to worry. It is oxygen in its standard state, so that is going to be 0. Hooray, one less number to include in the calculation. So if you write down all your parts carefully and do the arithmetic, it's not even worse than that. There's no algebra. We have to take the values and put them in properly. So for the heat of formation for carbon dioxide, we have the 393.5 kilojoules per mole, 1 mole of CO2. Add to that 2 times the 285.5 for the heat of formation for water, but notice the negative signs on each of these things. Don't get them mixed up. And then subtract from that the set of terms for the reactants, which is the heat of formation of methane, and it was the minus 74.8 kilojoules. Again, notice that you've got negative signs side by side here with a bracket in between. Be careful that you use the signs properly. And when you do it, the first term simplifies now to 393.5 minus 571. That's what you get when you double the 285.5. So those are both negative terms. And then you will add the 74.8 to it to get your final answer. And now you get out your calculator and see if you can do the math carefully. All right, having put the math together, you will find the first term, when you combine those two negative values, is 964.5. Does that look good? Add to that the 74.8, and the answer I got, I hope you get the same, is minus 889.7. Now, just think about it as a moment to check yourself. Should this be an exothermic process? For sure, because we have the combustion reaction here, and combustion should always be exothermic. And so the negative sign is appropriate, and we are glad that our numbers correspond in that fashion. All right, let's do another example. There's more examples to do. Let's use the standard heats of formation and calculate the standard enthalpy of the reaction for photosynthesis of glucose with combining CO2 and water to make the glucose with oxygen as a byproduct. We're looking for the heat of that process. We couldn't possibly calculate this in a very simple sense, but realizing that the overall energy change for separate steps gives us the energy change for this net process will allow us to calculate that value. So how does that work out? Well, what are we going to do? You'll look up numbers for all of these things so you won't know them automatically. Do not panic. And so what it is going to be, it's going to be the sum of the heats of formation of the reactants, the products, right? Products come first, and minus the heat of reactions of the reactants. Keep your eyes straight on this one. And so the products are going to be the glucose, the heat of formation of glucose, and oxygen. But the standard heat of formation of oxygen is going to be 0 because that's the element in its standard state. One less thing to put in. Subtracting the numbers for the reactants, then notice that you have to have 6 times the standard heat of formation for the carbon dioxide and 6 times the standard heat of formation for water. Otherwise, the numbers will not be correct. Having looked up values elsewhere, and you could flip into a different place and find them in your book, the standard heat of formation for the glucose is going to be this value 1,273 kilojoules released per mole in 1 mole. So we got the 1 here, which is just obligatory, but doesn't really change your calculation. Subtract from that 6 times the value of the heat of formation for CO2, which you can look up in another slide in another place, and 6 times the heat of formation of water. Putting all the numbers together, doing the math carefully, realizing that we are subtracting this whole second set of values from the first one. The answer comes out to be 2,802 kilojoules. Now think about it. Formation of glucose, is that likely to be an endothermic process? Yes. Endothermic, building a big molecule is going to require energy. It's an endothermic process overall. Okay, let's do another example. The more the better. But let's also talk our way through this one. I apologize, I was going to back up and do that. So how do we make sense of Hess's law being used with these standard heats of formation, and why does this method actually work? So what we're looking at is the individual steps that we literally have put together to make this all happen. What we do first is we reverse the reaction. We look at the reaction and reverse the sign on the standard enthalpy change for making CO2. Because the making of CO2, we can find that in a chart, and it has a negative 393 kilojoules per mole reaction, but we need CO2 as a reactant. So we'll reverse the reaction, and in so doing, we reverse the sign, and now we have a positive 393 for the reaction in reverse for CO2, turning into carbon plus oxygen. Now, it's only a theoretical reversal. We're not having to do it in a test tube or whatever, but this is how the mathematical approach to this works. So that's the first thing. We're going to combine this process of CO2 with making carbon and water or oxygen with some other steps. Well, next we will also have to multiply by a coefficient, because it's not just 1 CO2 that we need in the net process, we need 6. So we're going to multiply by that standard enthalpy change, then also by the 6. So 6 CO2 making 6 carbon and 6 oxygen has to be 6 times the change in heat, because this initial one was per mole in the reaction as shown. And so this becomes 6 times the value, so 2,300 something kilojoules. That's what we do to get the CO2 in our net reaction properly. And the reversing the reaction of number to get 6 waters, well, what do we have to do? So thinking about the heat of formation of water is going to be hydrogen plus oxygen combining to make water as a liquid, and that's what we want in its standard state. We'll look it up in a chart, and it's 285.8 kilojoules per mole. You're going to run into this number a few times. You might begin to become familiar with it. And if we're not going to use it as water on a product side, we'll flip the reaction around and reverse it to change the sign. Now it's a positive 285.8 kilojoules per mole. If you're thinking of the water dissociating to make hydrogen and oxygen, not that we're specifically doing it here, but mathematically, our standard heats of formation can be used in reverse. The reverse of a reaction has the opposite sign for the enthalpy change. All right, that was part 2 of the things we're putting together. What do we have to do next? Oh yeah, again we have to multiply by a coefficient, don't we? Because water is times 6 in this particular process. So we multiply the coefficients by a factor and the standard enthalpy change by the same factor. So 1 water and 1 hydrogen and half an oxygen become 6 water, 6 hydrogens, and 3 oxygens, and 6 times the enthalpy change, because the first one again was per mole, and now we have a much bigger number, 1714.8 kilojoules for 6 water molecules being used. All right, next one. So we're still trying to come up with the total overall process. We got the number up there at the top in the red. We're putting this all together. So what have we added together? And this is like doing Hess's law. The separate steps add up to making an overall process that we can calculate an enthalpy change by mathematics rather than doing it in an experimental way. So we're combining the various steps. Carbon plus hydrogen plus oxygen. We had 6 carbon and 6 hydrogen and 3 oxygens from those previous equations on the previous slides. Are going to be reactants that combine to make the glucose. Well, that would be making glucose from its standard states. It's carbon and hydrogen and oxygen, and would give us the right numbers of each of those. That's the standard heat of formation for the glucose. Then the next piece is the CO2 reaction that we multiplied by 6 to get CO2 turning into carbon plus oxygen. It's the opposite of the heat of formation of CO2, right? And so we turned it in reverse and multiplied by 6, and we ended up with 2,361 kilojoules. The third step here is the 6 water molecules being in reverse of its standard heat of formation being taken apart to make hydrogen and oxygen. And so its standard heat of formation, well, it's not formation now because we did it in reverse, so those aren't really proper. We reversed it, but we add 6 times as much as the original value, and we flip the sign. So combining all of these things to make the total reaction of 6 CO2 and 6 waters to make glucose plus 6 oxygen, combine all of those delta H values, and there you have it. So that's effectively what we've done in our delta H calculation, where we were subtracting the sum of the heats of formation of the products, subtract from that the sum of the heats of formation, subtract from that the heats of formation of the reactants. Remember, we changed the sign on those two, and so that's why adding these up, it gives you the same result. Let's do another one. How do we determine the heat of formation of carbon monoxide? Turns out it's a reaction that's hard to do. The standard heat of formation of carbon monoxide means you'd combine carbon and oxygen, and it's difficult to do it because carbon and oxygen are going to combine to make CO2 very readily anyway. So you're going to know about have to figure out how that would work in a mathematical sense. The standard heat of formation reaction for carbon monoxide would be then combining graphite with oxygen. It only takes half a mole of oxygen in this case to make our carbon monoxide. We're going to use Hess's law and think in terms of the known steps, and we're going to find some values in a table from the textbook or some other chemical resource. So first reaction, we can find the heat of formation of CO2 is making carbon as graphite with oxygen gas to make CO2 gas. We look it up. We've seen that number actually. The heat of formation for CO2 is given here. Then, and that's been experimentally determined. It has been. But then we can also look at the formation, another one, the reaction in the next step is not heat of formation, but it's experimentally determined to take carbon monoxide and add to it some oxygen to make CO2 and have a delta H value. Again, this won't be shown in a table of standard heats of formation because this is not a standard heat of formation. It's not making it from elements. So you'd have to determine this one experimentally. And then what do? We're going to have to take that reaction in reverse to end up with a net process that doesn't include CO2. So reverse that one and put CO2 now on the reactant side instead of the product side, because what we want to end up with is this process here, and there's no CO2. We've got to get rid of it. We're going to use this reaction that has graphite in it as well. So graphite has to be on the left side, and the CO2 has got to be canceled out by using this reaction number 3 with CO2 on the left. Then where are we? Oh, notice then, of course, then when we reverse the reaction, the change, enthalpy change for that reaction has the reverse sign. You combine the two, and whoops, sorry, let's do it here. And what will we get? So 393.5, subtract negative value, add to that 283 kilojoules, and what should we get? Hopefully you can do that with your calculator. And we should end up with a value of minus 110.5 kilojoules per mole. Now I'm going to think about it in a graphical sense. This is in Hess's law thing of combining all these parts will give us something where you combine the delta H's and end up with the right thing. So notice that we're combining reaction 1 and reaction 3 to get the intended reaction at the top. So we have the graphite on the left. Do we have half of an oxygen by the time we combine the two? Well, we have half of an oxygen because there's one here on the left side and a half on the right. That leaves us half on the left. So graphite is remaining when we combine these two. And half a mole of oxygen, which is a gas certainly. And then what's left in these reactions? Well, looking at reaction 3 and reaction 1, the CO2 can cancel out now because it occurs on both sides, and then the product then remaining is only carbon monoxide gas. So the sum of the heats of these processes gives us, by Hess's law, the overall enthalpy change for the net reaction that we're looking for. Now, again, a graphical representation for this is on the next screen, where we're looking at how this can be envisioned. So we're trying to determine the enthalpy change of graphite plus oxygen in making carbon monoxide, which is hard to do. And so what we're going to be looking at is effectively this process between graphite and oxygen making carbon monoxide. Notice that this shown is a whole mole of oxygen, but it results in half a mole of oxygen. So effectively, you're using half a mole of oxygen to get from the top to the carbon monoxide step. So, but again, why do these energies make sense? So if you're going to take graphite plus oxygen to make carbon monoxide and some oxygen, but then carbon monoxide plus oxygen to make carbon dioxide at the bottom here, the sums of those two processes should give us the total enthalpy change from making graphite with oxygen into CO2. And so if you subtract this value of the portion that we're not using to get to carbon monoxide from the other one, you should get 110. Does that look credible? I think it does. So graphite plus half a mole of oxygen makes CO2, carbon monoxide. If you combine carbon monoxide with half another mole of oxygen, you get carbon dioxide. And so the overall process is the graphite plus oxygen, top to bottom, then making CO2. And what part we want was only the part from the first step, the one that we weren't able to measure. All right, let's do another example. Many examples are helpful. There's a lot of things to pay attention to. Calculate the standard enthalpy of formation of carbon disulfide, which in this case is taken as a liquid, given that what? We can make the heat of reaction of graphite with oxygen to make CO2. That's a standard heat of formation again. That's what standard heat means. That little zero indicates that. And then sulfur plus oxygen to make SO2, sulfur dioxide. S rhombic is a standard state of sulfur, which we haven't discussed, but it's one of those curious forms of sulfur. It has a few. And the heat of formation for that process can be used to calculate the standard heat of formation of the liquid CS2 if we use one more equation. The CS2, carbon disulfide with oxygen, can react to make CO2 and sulfur dioxide, and that's the third reaction here, with a heat change enthalpy for that reaction shown as well. It's not a heat of formation here because we're not just making something from elements in the standard state, but it's a standard enthalpy change for things in standard states. So what do we have to do to get there? Well, we'll put the enthalpy of formation reaction for carbon disulfide. In other words, carbon combining with sulfur in their standard states to make carbon disulfide. So take the two forms that we know of are being standard states for those two elements and make the liquid that we're looking for. Then we're going to add the given reactions of, as shown at the top, so that the result is the desired overall reaction. So what will we do? We need to find graphite. So graphite plus oxygen is going to be making CO2 from that first reaction. Call that reaction A for this purpose. And that delta H value is known. So that gives us a reactant of graphite that we want. And so then now we need something with the sulfur in it as a reactant. Okay, so we'll use reaction B with sulfur with oxygen to make SO2. But again, we have to pay attention to the stoichiometry here. There's a 2. And this is a really common, easy mistake. You'll have to multiply this whole reaction by 2 because we need 2 sulfur in our net process to get the right answer. And in so doing, we better multiply our delta H by 2 as well. What does that give you if you take 296.1 twice? A simple calculation will give us 592.2 kilojoules for 2 moles, because that other one was for 1 mole, correct? Now, what do we do next? Okay, now we need to find CS2 as a liquid. CS2 as a liquid in an equation. Well, that would be the third choice, right? And in the third choice, the reaction has CS2 liquid, carbon disulfide liquid, as a reactant. But we're going to switch it around, reverse the process, as shown next here, to put carbon disulfide as a liquid as a product. And in so doing, we change the sign of the enthalpy change, now that we're considering it in reverse. But we don't have to change any coefficients here. Thank goodness. That makes life easier. And then it puts CO2 and 2 SO2 as reactants, and carbon disulfide as a liquid, as a product, and some more oxygen. Just using reaction C to give us the third step here. Now we should be ready to combine these things and see how it all comes together for the net process that we're interested in. So we have CS2 as a liquid in our product, which was the intent. Combining all the pieces and the steps. What can we combine and what can we cancel? All right, so oxygen occurs on the left side, but guess what? We can cancel out 1, 2, 3 oxygens with 3 oxygens on the product side. They don't show up in our net process that we're looking for. Good. What else will cancel? Keep looking. Well, there's some carbon dioxide. We don't need that in this total overall process because it occurs in these sets, these 3 combining reactions, in one instance as a reactant, one instance as a product. And the third one is SO2. Sulfur dioxide is a reactant in one process and a product in another. So overall, it's not a net change. And the net process then gives us the graphite with the sulfur to make the CS2 liquid using these thermochemical calculations. And Hess's law tells us we can sum the series of the delta H's of the individual steps to give us the delta H of the overall process. Here goes the numbers. Oh, apologies for the little icon in the middle. And if you put it in your calculator carefully, we should be able to come up with the proper value. Wow, a lot of steps and a lot of ways to be careful. All right, let's see if we can find another example or two. Benzene, burning in air to make carbon dioxide and liquid water. How much heat is released per mole of benzene combusted? The standard enthalpy of formation of benzene can be obtained from a table. Here's a value provided for us. We also need the standard heat of formation for CO2, which we have seen on occasion, and water, because it keeps showing up in combustion reactions from that table in the text. So what do we have to do first? And we're going to use delta H values, delta HF knots. Yeah, so we call those standard heat of formation values. So the balanced reaction. Oh, yes, we have to come up with that one and get it right. Well, let's put in some numbers. There is more than one way to balance this equation. The first way that I came up with as I worked this through, I realized that we would need to have, we have the right number of, we put 6, on front of the carbon on the CO2. We have to have more hydrogens and put 6, we need some more hydrogens on the right. We need a total of 6, so put 3 on the water. But then we have to figure out how many oxygens there. Oxygen over on the left side, we have 12 plus 3 is 15. And that means in order to do that with oxygen as O2, you would end up a funny coefficient. So perhaps a more preferred set of coefficients would be to use this with a whole number set of coefficients, in which case we'll double everything. So we would use 2, 7, 12, and 6 in our balanced equation. All right, continue. So I did it wrong. That's not 12. It should be 15 over 2, not 7 halves. Let's fix that. I wrote the wrong one in here. So, yeah, put the right one in. 15. There we go. All right, now we got the right numbers. And like I said, there's a lot of places to make mistakes here. Sorry about that. 7.5 as opposed to 15 halves. That's what I did wrong. Okay, what next? The heat of reaction is going to be the sum of the heats of reactions of the products. Subtract from that the heats of reactant of the reactants. Wow, be careful. So the heats of reaction of the products would be the CO2 and water. So we have to multiply them by their stoichiometric coefficients, put 6 on the water and 12 on CO2. Subtract from that the heats of reaction formation, of the reactants. So it's benzene, and there's 2 of them, so make sure we put the 2 in or we'll make mistakes. And then the oxygen, oh well, hooray, the heat of formation of water, or sorry, oxygen is 0. It's an element in its standard state. Don't have to put any more numbers in here. But look at how many places you have to plug in things correctly to get it right. Okay, so the numbers were provided in the previous slide, and we had 393.5 for the CO2 formation times 12, 285.8 for the water standard formation times 6, and then subtract from that. Notice this is a big bracket here. All those combined, those first ones combined, subtract from that 2 times the heat of formation of the benzene. And if you can do the math correctly, that's the overall heat of reaction for these processes as shown. But guess what? We have one more line here. That is for 2 moles of the benzene. And so what we're looking for per mole of benzene combusted, this is for 2 moles of C2H6. So we aren't done yet. So if it's 2 moles of C2H6 benzene, then that number we got there, which appears to have been transcribed incorrectly, sorry, that should be a 5. Not my fault, I borrowed this. 5, 3, 4. Well, you get the idea. Divided by 2 should give us the proper answer. So beware of these kinds of places that coefficients are going to be required, and oh my goodness, you'd have to be careful. There's a lot of opportunities to miss something and make an error. Let's look at another reaction example. Calculating the standard enthalpy of formation of acetylene, C2H2. It's used in welding torches as represented by the picture at the bottom. From elements, this one is less complicated than the last one. Good. So what else do we need to have to do this one? We're going to try to figure out the standard enthalpy of formation for acetylene from its elements, right? So carbon and hydrogen to make C2H2 takes 2 carbon and 1 molecule of hydrogen. And what else do we have that we can put together to come up with this one? So the heat of formation for CO2, we've seen that before. And the reaction of making water liquid, that's a heat of formation too. And we can use another reaction that hasn't been discussed before, but we can find it in a chart someplace. The combustion reaction for acetylene to make CO2 and water apparently has a value we can use as well from another table. Then we'll use Hess's law and combine the separate steps to come up with the overall process of this heat of formation of 1 mole of acetylene. All right, so graphite plus hydrogen to make acetylene. We're looking for the standard heat of formation. Graphite plus oxygen to make CO2. We're going to need this twice. So remember that the coefficients all have to be correct in the end, and that means we'll double the heat of reaction for that process. We'll combine that then with a process that puts hydrogen as a reactant, and in other words, water here is going to work for this process. And so no doubling of coefficients or anything else is needed. We'll just include the standard heat of reaction for that particular piece. Now we want CO2 to be twice because our first reaction, I'm going to call it reaction A, B, C. These 3 will combine to give us the net process if we put it all together correctly. reaction A has 2 CO2, so we better have to put 2 CO2s in our last reaction that we're going to be taking from the previous slide, and we're doing this one as half as much because we only need CO2 times 2. The reaction we were given was given with whole number coefficients, and so that would have a 2 in front of the C2H2. So everything from that reaction is now divided by 2, and we end up with a single mole of C2H2, but half as many kilojoules per mole. That's a little subtle. Be careful on these steps. So the delta H of formation for this process overall would be the sum of these things combined. Again, how does this work? Are we going to put all the parts together? So we want graphite on the reactants, so 2 carbon as graphite, plus what other reactants do we have? Well, we don't want any oxygen left over, do we? But we have 2 oxygens here and half an oxygen, but 5 halves here, so guess what? Thankfully, the oxygen is going to cancel. The next reaction is going to add the hydrogen that we want. So how many hydrogen were there going to be? We hope there was only 1. And there is only 1 on the left sides of each of these reactions, so H2. And now we have to make sure that these extra reactants are no longer an issue. Well, there's 2 CO2 in reaction C, but there's 2 CO2 in the product of reaction A. Reaction B has water as a product. Reaction C has water as a reactant. Those cancel out. And now we have C2H2, our intended acetylene, as a product, and nothing else left in the product side. So we combine the heats that are shown here. So the 2 times 393.5, the 2 negative, that was the first one was negative, the second one is negative 285. We're adding all these up, and half of the third one to get our final answer, which turns out to be 226.6 kilojoules per mole. Now, is this reflecting an endothermic or an exothermic process? Anytime the value is positive, we have an exothermic reaction. But does that make sense? Yes. Making bonds, putting together carbon and hydrogen to make acetylene, making bonds is going to be endothermic. Making bonds, making a compound is going to be endothermic characteristically. All right, let's see if we've got another example to look at. More examples the merrier. I hope these are helpful to someone. Here's chemistry in action. A bombardier beetle uses hydroquinone and hydrogen peroxide to make something called quinone and water, and it squirts it at its enemies in a self-defense mechanism. So hydroquinone is apparently C6H4OH2. It's aqueous, and it's going to combine with hydrogen peroxide to make quinone. It's got the formula shown on the right side of the arrow, which we don't need to understand. It's just given that information. The balanced equation results in having water as a product. We want to figure out the heat of that reaction. So what would we do? We have to know some heats of other processes. We can combine these and come up with an overall heat change. So the hydroquinone reaction first we'll do in water can be found to have a reaction that creates the quinone plus hydrogen, and there's a delta H provided for that reaction. Then you can find hydrogen peroxide decomposing and making water and oxygen. There's a delta H for that process as well. And then we can use the formation of water, the heat of formation of water, which is hydrogen with oxygen, to make water as a liquid. We've seen that number somewhere, and this time they're rounding off the 85.5. And how do we combine these to come up with a heat overall for the process that we want? Can you combine them as is? Hopefully. Let's check. So if we're doing this correctly, one reactant needs to be the hydroquinone. So this one is the only one is on the left. We need to have peroxide on the left. There we go. And we need to have the quinone on the right and 2 water molecules. Well, if we take these 2 combining B and C reactions, we've got 2 water molecules. But what do we do with the other parts that don't belong here? Well, let's check it out. We have hydrogen as a reactant in reaction C, as a product in reaction A, half an oxygen mole in 2 places. That cancels out to give us the whole overall process intended. So therefore, we can add up the different values provided, the 177 minus 94.6 minus 286, and we get minus 204 kilojoules per mole. This is a very exothermic process. In other words, when this beetle is making this squirting stuff, it's going to be hot. All right. So from here we'll go into the next recording.